For this example, I would like to find an equation of the plane that is tangent to this multivariable function x cubed plus y squared minus xy at the point 1, 1, 1. So that means when my x is equal to 1 and when my y is equal to 1 and my c is also equal to 1. So before I do the math, let me actually show you what the picture looks like. So this surface, this is the graph of the function that we were looking earlier, x cubed plus y squared minus xy. And I have this blue point 1, 1, 1, which is a point on the graph. So I would like to have a surface. I would like to have what? I would like to have a plane that is tangent to this surface at this blue point. Now let me actually show you right away what this plane is going to look like. This plane, the blue plane, notice how it kind of tangent to my green curve. So this blue plane is basically what I'm looking for. And we kind of see here already that the equation for the blue plane is going to be c equal to negative 2 plus 2x plus y. But how would we go about and find this plane numerically? So let's take a look. Now, remember in 2 dimensions, if I want to find a tangent line to a function, what we need to do is that I need to have a line that goes through this point and has the same slope as the function. And this is going to be the strategy that I'm going to use as well. So I have the funny looking surface that we were looking at earlier. I have the blue point on this surface, and I would like to find an equation of the line that would be tangent to this surface at the blue point. So what I'm going to do is this. I want to make sure that my blue plane here, it has to go through. It has to pass us through the point 1, 1, 1 that we have earlier. And it actually also needs to have the same slope as the surface. It needs to have the same slope as the f of xy at the point 1, 1. And at the point 1, 1, I mean my x is equal to 1 and my y is equal to 1. So if I could find a plane with this property, then this plane would be tangent to my function at the point 1, 1, 1. So first thing first, I need to find the slope of my f xy at 1, 1. So that means I need to find the partial derivative of this guy with respect to x and with respect to y. So let's see, my f sub x partial derivative with respect to x. This is going to be just, let's see, 3x cubed. And then the derivative of y squared is gone because y is a number. Derivative of negative xy is going to be just negative. It's going to be just negative y. And partial derivative of f with respect to y is going to be x cubed is gone. Y squared becomes 2y. And then negative xy becomes negative x. Now then, I need to find these values at the point 1, 1. So all I have to do is just plugging 1 in for x and 1 in for y. So my f sub x at the point 1, 1 is going to just be 3 times 1 minus 1. So that's a 2. And my f sub y, partial derivative with respect to y at the point 1, 1 is going to be just 2 times 1 minus 1. And that's going to equal to just 1. So now, I'm looking for a plane that goes through 1, 1, 1, and the slope at the point 1, 1 with respect to x is 2, and the slope at the point 1, 1 with respect to y is 1. So let's recall what is the equation of a plane again. The general equation of a plane is just ax plus by plus c is equal to d. So if I were to move x and y to the other side, and let me actually also divide c on both sides, I'm going to have my c is equal to d over c minus, let's see, a over cx, a over cx, a over cx again, minus d over cy. So here, this is a general form for the equation of a plane. Now then, I want the partial derivative of c with respect to x to be equal to 2 at the point 1, 1. So let's actually compute the partial derivative here. So my partial derivative, dc by dx, this is going to equal to, well, partial derivative of c with respect to x, so I ignore the y. d over c, this is a constant, so it's gone. Derivative of negative a over cx is just going to be negative a over c. And then negative b over cy is gone because y is a number. And then let me also do derivative of c with respect to y. dc by dy, this is going to be, let's see, d over c is a constant, so it's gone. Negative a over cx is a constant, so it's gone. dz over dy is going to be just negative b over c. And now, because I want this little term here to equal to 2, because I want my plane to have the same slope as my function, and I want this guy here to equal to 1, because once again, I want my surface, my plane, to have the same slope as my surface. So that means I'm gonna want my negative a over c to equal to 2. And I'm gonna want my negative b over c to equal to 1. So this thing equals to 2, and this thing equals to 1. So that means my c now equal to d over c. So I don't know, wait, let me my c, right now it looks like d over c plus 2x plus 1y, which is plus y. Now, I still need to figure out what is this d over c, but I have one extra information left. I knew that my plane need to pass through 1, 1, 1. So if I plug in 1 for x, 1 for y, and 1 for c, I will be able to figure out what this thing in the red box is. So if I do the plug in, I'm gonna have 1 equal d over c in the red box plus, let's see, plus 2 and then plus 1. Now then, so I know this red box thing, it just needs to equal to negative 2. So my d over c, this has to equal to negative 2. And that means I can conclude that the equation of the plane that is tangent to this function at the point 1, 1, 1 is going to be just c equal to negative 2 plus 2x plus y. And indeed, this is the surface, this is the plane that we were looking at earlier.